we now turn our attention to the simple pendulum. And for the simple pendulum, there are going to be a few assumptions. Okay, now first things first, a pendulum that we're going to describe is that of a mass M suspended by a length of string L from some frictionless support. Okay, so the whole idea of the pendulum is that when I pull the mass away from its equilibrium position, right? So the equilibrium position is the vertical. Gravity is trying to pull it straight down. This is where the pendulum wants to be, but when I pull it back in an arc and then I let it go, it'll swing back and forth between these two endpoints. Right? And by the way, these two angles will be the same, despite whatever imperfections are in my drawing. Okay, so the simple pendulum has a couple of properties. Number one, I shouldn't say properties, I should say assumptions. Okay, so let's label these the assumptions of the simple pendulum. Number one, the string is massless. This is usually achieved by using a very, very light string or rope compared to the weight of the mass. And the idea here is that the string is not contributing any moment of inertia to the system. Okay, you don't want your mass to be or you don't want your string to be influencing the system other than being the thing that your pendulum, what we call the pendulum bob for the hanging mass. You don't want the mass to be doing anything else other than being the thing that the bob is hanging from. Okay, and then number two, the angle is small. The initial angle of displacement is small. Okay, so with these two guiding principles, we can derive the properties of the simple pendulum as follows. What I'm going to do is I'm going to draw a free body diagram, and I'm going to orient my axes along with the tension and perpendicular to it. Okay, so my y-axis is going to be here, my negative y, and my x will be perpendicular to that, and my minus x will be up here. Okay, now what forces are acting on the pendulum bob once you release it? Well, there's only two, right? Gravity and tension. So gravity is going to act straight down toward the ground, and your tension is going to be acting up the rope. Okay. Where have we seen this before? Well, this harkens really similarly to the inclined plane, right? And it actually, the inclined plane is the motivation for why we rotated our axes in the first place. But if you remember what we did with the inclined plane, we then broke gravity up into its constituent components, as you must when vectors don't lie along axes. You typically want to get their components. And I'm going to make the claim, I'll prove it here in just a moment, but I'm going to make the claim that this angle is theta. Okay, so it's the same theta as in this diagram. All right. Now, this component is then going to be mg cosine theta, and this component is going to be mg sine theta, right? And I should have made my tension and my mg cosine a little bit longer to fully effectively complete the right triangle, but you get the idea, okay? Now, so here's the key, right? If I apply Newton's laws, I need to sum up the forces in the y direction, and I need to sum up the forces in the x direction. So in the y direction, we have t minus mg cosine theta. This must equal 0 because instantaneously the pendulum is not accelerating in the y direction at all. Okay. Now, what's going to happen as the pendulum is swinging, this is where our convention will kind of break with the inclined plane. We're going to let this coordinate system rotate as the pendulum is swinging, right? So when the pendulum is at the equilibrium position, then this would be a typical vertical horizontal Cartesian system. And then as it continues to swing, the coordinate system will rotate accordingly, right? So under that condition, the y-axis, the net force along the y-axis is always going to be 0. And the net force along the x direction is mg sine theta, and that has to equal ma. Right? Now, so let's prove that this angle is indeed theta. Right? So, how do I prove this? Well, let's look at this support. So remember, I can shift verticals and vectors in my coordinate system with impunity. So let's suppose this support is right here. Okay, so then this would be L right here. Then my vertical would be right here. And this would be theta, right? But if I draw another vertical right here, then that by alternate interior angles, this is also theta, and then by the vertical axis theorem, this is theta as well. Okay, so the theta in our free body diagram is the same as the angle that the pendulum has been pulled back. Right. So the motion of the pendulum is going to be dictated by this x direction, the x component of our net force, right? And unlike the spring, notice that the mass cancels out, right? So we have A is equal to g sine theta. Now, I'm going to put a negative sign in here, even though according to our free body diagram, it shouldn't necessarily be in there. The justification for this is intuition. And that is when you build a pendulum and you pull it back, you watch it swing back and forth. You watch it oscillate. Therefore, the force acting on the pendulum must be a restorative force. And therefore, it must follow Hooke's law. Now, so the whole point is to transform this equation into something that looks like Hooke's law. Okay, so we want to transform our equation a equals negative g sine theta into an equation of the form the second derivative of our function with respect to time equals a negative sign with some constants times our function. Well, we're already on our way, right? We've already got a negative sign. We've already got g as a constant, but now we have to decide what we want. And what you can quickly realize is because theta now is the thing that's changing with time, if I think of this problem in polar coordinates, then I don't have to worry about x's and y's. So I need to figure out how to write my acceleration in polar coordinates. And then under that model or that paradigm, now theta is our function of time. Okay? And so the way to think about our acceleration is think about some arc length. Okay? As the pendulum swings, it's going to swing through some arc length per time. And from geometry, remember that there's a fundamental relationship between arc length, radius, and angle, which says that angle is equal to arc length divided by radius. Okay? Now, again, this only works when you're in radians. Okay? And so, what we can say is that S is equal to L theta. Okay? So my position function is my arc length, while my angular function is going to be theta, but this is a positional acceleration or a linear acceleration. Okay? So my angular, not my angular, but my linear acceleration is then going to be the second derivative of my arc length as it changes with respect to time. Okay? And now I can translate this into my polar coordinates by taking the second derivative of L theta, substituting in for S equals L theta. And what I'll notice at this point is that L is constant, right? So I can think of the path of my pendulum as being part of this circle with the support right in the center. And therefore, L will act as the radius of this circle, and S will be the arc length, and theta is the angle that it subtends. Okay? And so, with that kind of thought process, what we can see is that L is constant. So it can come out of this derivative. And now we're taking the second derivative of theta, which we must because theta is our function of time. Right? So now we have our function, or our equation looks like this. L d squared theta dt squared is equal to negative g sine theta. And now we're actually kind of starting to see something that looks a little bit like this. There's still the sine theta we need to handle, but actually let me come back here one more time. This is where we're going to employ the second of our assumptions, that the initial angle of displacement is small. And what we're going to do with that is we're going to apply what we call the small angle approximation. And the small angle approximation says that for small theta, Sine theta is approximately equal to theta. Really should make this an approximation. Okay. For small angles, sine of theta is approximately equal to theta. And if you think about it, this should make some sense. If I have a right triangle with opposite side S and hypotenuse L and angle theta, then sine theta is equal to S over L. But if I have a circle with L as the radius, and I make a small angle theta, then my arc length S will be here. If I make this small enough, if I make theta small enough, then S approaches a straight line. But this equation, S equals L theta, is still true. And therefore, if I look at this equation, S equals L sine theta, then I can set these two equal to each other. And I see that L is equal, or my L's cancel out, and theta is approximately equal to sine theta, under this condition that if theta is small enough. Right? And you can prove this to yourself. Now, this must be in radians. Okay? Theta must be in radians, but you can prove this to yourself. If you take the sine of 0.1, what do you get? You get 0.09983 and some change. Okay? This is under 2% different. I'm sorry, under 0.2%. Now, 0.1 radians is about 5.73 degrees. So even at 10 degrees, you're still within 1%, where sine of theta would be 1% off from theta. Okay, so the small angle approximation we usually take as valid up to maybe about 20 degrees. That's about the maximum you'll see anybody take it. So for small angles, like if I pull a pendulum back 5 degrees or 10 degrees, then I'm within this small angle regime and within the ability to measure things with typical stopwatches. I can't really measure these, differences of being off by 1%. With a typical stopwatch with just a few trials. It would take hundreds and hundreds, if not thousands of trials to really start to determine the difference between sine theta and theta. Okay, so we take this small angle approximation, set sine theta equal to theta, and divide both sides by L, and we get the second derivative of theta with respect to time is equal to negative g over L theta. And now this looks like Hooke's law. Right? So remember, with Hooke's law, our angular frequency was k over m, and our frequency was 1 over 2 pi k over m, and our period was 2 pi m over k. For the pendulum, if we look at the exact same kind of equivalencies and draw the same parallels, we see that our angular frequency is equal to g over L. Okay, now let's pause for a moment and think about this result. The longer, well, okay, so my angular frequency is my radians per second, and my normal frequency is 1 over 2 pi square root g over L. Now, for the moment, we're going to assume that we're on Earth, so g is constant at 9.8. And what this is telling you is that the longer I make my string, the lower my frequency, the fewer cycles per second. And if you think about it, that should make some sense. If you've ever watched pendulums, you know that a really short pendulum can swing really, really rapidly, and a really long pendulum will swing very, very gradually. So you will have a much higher frequency with short strings than you will with long strings. Okay? And it usually makes a little bit more sense intuitively when we put this in terms of the period. So if I look at these two equations, okay, they are just reciprocals of each other, so F and T have to be reciprocals of each other. So the period of a simple pendulum is equal to L over G. And here we can see that the longer I make my string, the longer my period will be. Okay? So these are your three fundamental results for simple pendula. Okay? The angular frequency is your gravitational field divided by your length. Your frequency is that times 1 over 2 pi, and your period is 2 pi times the square root L over G. Now, to move away from the Earth, okay, if I move away from the Earth, let's go out into empty space. In empty space, G is approximately 0. So I build this apparatus and I pull my pendulum back. What will happen? Well, if there's no gravitational field, there's no gravity to pull on it, no net force. So if I pull it back and hold it there, it will remain stationary. What happens to my period if I plug in G equals 0? T goes to infinity. It would take an infinite amount of time for this pendulum to complete one cycle. Which, of course, if it stays stationary, is exactly what you would expect. And so, this formula makes sense not just when you change your lengths, but when you also change your gravitational fields as well. Okay? So, just wanted you to be aware of that. But this is the formal derivation of the pendulum and the results for the angular frequency, and period of your pendulum. Okay? So in the next video, we will look at stability and stable equilibria, and how to get small, the frequency of small, or I should say the frequency of oscillations for small displacements. Okay, that's what we will do in the next video, and we will see you then.